Okay, hello everybody, and welcome to the conference on singularity formation and propagation in gas dynamics. As you see, I'm filling in for Leo because he's still traveling just for the morning. Okay, so our first talk will be by Sandine from UC Berkeley, and he's going to talk about accelerated singularity formation, shock formation in Euler-Poisson systems.
Yeah, but this working? Okay. Okay, yeah. So the title of my talk is on accelerated shock formation. For the energy critical Euler-Poisson system. And everything I'm going to talk about today is joint work in preparation with Mihir Hedrick. He's here, and we'll be talking next. Juhi Jang at USC. And Sung No, UC Berkeley, my advisor. Okay, so today I'll be talking about the Euler-Poisson system. So I'll start by running down the system. So this is describing a compressible gas. And so rho from R across R3 to R. This is the mass density. And I'll assume always that there's no vacuum, so the density is always positive. And U will be the velocity. So this is the velocity of the fluid. Okay, and we're also going to assume that the gas is isentropic. So there's no entropy, and that the pressure is P equals rho to the power of gamma, where gamma is some fixed constant, which is the adiabatic index. Okay, and I'm also going to assume that the gas is self-gravitating according to Newtonian gravity. Okay. So this gives the following system of PDEs. So we have concentration of mass is dt rho plus divergence of rho u equals 0. Okay, and there's also contribution of momentum, which I'm going to write as dtu plus u dot grad u plus 1 over rho gradient of rho to the gamma. And this will be equal to the pressure per unit mass, which in this case is negative gradient of phi, where phi is the gravitational potential. And phi satisfies the Poisson equation that Laplace phi equals rho. And so here we're going to choose constants, so there's no pi's there. Okay. Yeah, this is what I'm going to talk about whenever I say Euler-Poisson. I'll also always, so in this talk, everything will be in radial symmetry. And so in particular, the velocity vector field will always just be some scalar u of tr times dr, where this is just the outgoing radial derivative. Okay, and so there's a couple of conserved quantities for this equation. And two main ones, which are going to matter a lot, are the mass and the energy. So the mass is the integral of rho t and x dx over R3. And the energy has a couple parts. So there's the kinetic energy, which is 1/2 rho u squared, plus the energy due to the pressure. You get 1 over gamma minus 1 rho to the gamma. Then there's also the gravitational energy. And so here we have a minus 1/2 gradient of phi squared dx. And in particular, there's a negative sign here. And so the energy is not coercive. And this is sort of corresponding to the fact that gravity is sort of causing things to try to collapse. And so this is in contrast to if you consider like an like electrons which are repelling from each other. Here everything is, and then in that case the sign would flip. But here everything's attracting, so we have negative sign here. Okay. There's also scaling symmetry for the system, which is going to sort of dictate what I mean by energy critical up there. Okay. And so if you do dimensional analysis, one thing is that from, I guess, either equation, you have the dimensions of u are dimensions of space over dimensions of time. And from the second equation, you have that units of acceleration. The pressure term, this is equal to the units of density over units of, so the density to gamma minus 1 over units of space. So that's this 1 over rho gradient rho to the gamma. And then from this term, this is equal to units of density times units of mass, or times units of space, sorry, because potential is density times space squared, and we take a gradient. Okay, and so in particular from this, you have the units of rho, or 1 over units of time squared. And then you can also kind of plug that into this equation then. I think if you do this correct, you get units of x, or units of time to the 2 minus gamma. And so what this sort of means for the equation is that if you take your mass and your velocity, and you replace it by 1 over lambda squared, rho t over lambda, to the, I'll put lambda 1 here, x over lambda to the 2 minus gamma, and you replace u by lambda to the 1 minus gamma, u t over lambda, x over lambda to the 2 minus gamma. This is a symmetry of the system, so this preserves the Euler-Poisson system. Okay, and if you do this rescaling, the mass density will go to lambda to the 4 minus 3 gamma times what the mass density was. And the energy density, or the total energy goes to lambda to the 6 minus 5 gamma times the energy. Okay, and so in particular, gamma equals 4/3. This is the mass critical exponent, or index, or exponent. Okay, and gamma equals 6/5. This is the energy critical. Exponent. And sort of when you're studying global dynamics for this PDE, you get a lot of qualitative changes that happen near gamma equals 4/3 and 6/5. This comes up if you're looking at sort of collapse or self-similar collapse. I think here is going to talk about this a bit. And there's also, okay, this also shows up when you look at steady states. And so that's what I'm going to talk about now. Okay, so steady states. And so you can think of these as stars because, okay, these are going to be cases where u equals 0 and your density does not change with time. And so if you look at the second equation, what you have is 1 over rho gradient of rho to the gamma plus gradient of Laplacian inverse of rho equals 0. So here I'm just going to write the potential phi as Laplacian inverse of rho and take it to the other side. Okay, if you use a chain rule here, this is gamma 1 over rho, rho to the gamma minus 1, gradient of rho plus gradient of Laplacian inverse of rho equals 0. And then now we can rewrite this as a gradient. So this is rho to the gamma minus 2 times gradient of rho. So this is gamma over gamma minus 1, gradient of rho to the gamma minus 1, plus gradient of Laplacian inverse of rho is equal to 0. Okay, and if you take now the divergence of this equation, what you get is gamma over gamma minus 1, Laplacian of rho to the gamma minus 1, plus if you take divergence here, you get Laplacian of Laplacian inverse. So here you just get rho equals 0. And then if you define the enthalpy, so W to be rho to the gamma minus 1, then when you do this, you get gamma over gamma minus 1, Laplacian of W, plus, and here you have W to 1 over gamma minus 1 equals 0. And this is now sort of the nicest semilinear elliptic PDE you can write down. And so this is the Lane-Emden equation. That's very well studied. Sometimes it's written as Laplacian of W plus W to the P equals 0. So maybe I'll say that when you write it like this, P equals 1 over gamma minus 1. Okay, and now, okay, I'm just going to summarize some well-known facts about this solutions to this equation in radial symmetry. So if you go to radial symmetry, in this case, you can write this as dr squared W or R drw. Okay, there's this gamma over gamma minus 1. Okay, maybe I'm just going to drop the gammas for now, plus W to the P equals 0. Okay, now this is an ODE, and sort of one thing you can do is you can sort of set some value at the origin and then try to solve to the right and see what happens. And it turns out what happens depends on which value of P you're at. And so in particular, if P is, okay, so if gamma is less than 6/5, so this corresponds to P being bigger than 5, what you get when you do this is, so here I'm going to graph W with respect to R. Your solution will decay, and then it will just always remain positive for all R. And as R goes to infinity, you have that W looks like 1 over R to 2 over gamma minus 1. Okay, and so this is not really a star because it's infinite extent. Okay, that's what happens if you try to solve this PDE. At gamma equals 6/5 exactly, this corresponds to P equals 5. In this case, there's an explicit, there's a closed form solution, which is exactly, okay, up to maybe some constants. W is 1 over 1 plus R squared. That's the 5/2. And so qualitatively, it looks like this. In this case, as R goes to infinity, you'll have that W looks like 1 over R to the 5, or just, sorry. I think here it should be 1, or 1/2. So here W looks like 1 over R. And in particular, there's kind of this jump in this decay rate that happens, because if I were just to plug in gamma equals 6/5 here, here you would get, or sorry, sorry, this is P minus 1. Sorry about this. That should be P minus 1. And so if you plug in P equals 5 here, you get 1 over R to the 1/2. And here you get 1 over R. Okay, so this is sort of much faster. And so you're kind of approaching the vacuum state very fast as you go to infinity. And finally, for gamma bigger than 6/5, this corresponds to P being less than 5. In this case now, if you solve this ODE from the origin, then what happens is your solution now hits the x-axis, or the r-axis. This is W, and this is R. And so this gives rise to finite stars, extent stars. Okay, and one thing I want to comment is that here, the star will obey the physical vacuum boundary condition. Which is important for well-posedness if you're looking at sort of dynamics where you perturb this. But the point is that maybe you should not think of this as anything really singular from the perspective of Euler-Poisson. And so here we see that this exponent gamma equals 6/5 is sort of this threshold between sort of these stars with very slow tails and the finite extent stars that corresponds to this energy critical exponent. And in fact, the mass critical exponent also has a role when it comes to looking at the stability of these things. And so in this case, if gamma is bigger than 4/3, what happens is that the star is linearly stable. And this is due to Lin, and I'm going to sort of cite more sources later. And if gamma is less than 4/3, the star is linearly unstable. Okay, and so Yeah, so this is just maybe some background on the dynamics of stars. And so what I'm going to talk about in this talk is sort of what happens if you perturb this exact star, which is gamma equals 6/5. And one way to think about this is that this is a very nice solution to the Lane-Emden solution system, as it has, because it decays so fast, it'll have finite mass and finite energy. And it's sort of, but it's also kind of nice in that there's no vacuum, but it's sort of as close as you can get to vacuum without having to sort of deal with the problems of doing math with vacuum. Okay. So this talk. Dynamics for gamma equals 6/5, and rho near what I'm going to call, so the Lane-Emden star, so rho LE. So in this case, when gamma is 6/5, you have that W is rho to the 1/5, so rho is W to the 5th. So rho LE, this can be 1 over 1 plus r squared. It's the 5 halves power. And so it decays like r to the 5th as r goes to infinity. So in particular, this is integrable in space. On the other hand, if you were a little bit above this threshold, then here this would become a 5 halves, and it's no longer integrable over R3. Okay, and so the first step to understanding this dynamics is you can linearize the problem about rho LE. So I'm going to linearize. So the Euler-Poisson system in this case, so dt rho plus divergence of rho u equals 0, and dt u plus u dru, plus, okay, actually I can put a 1 over 18 factor in front just to make things nice. And then you can write this term, so this gradient of, or 1 over rho gradient of rho, if I sort of use this trick, I think you end up getting, okay, so there's some, okay, maybe I should just not worry about the constants. Okay, I think if you do this right, you should get 1 over 5 here, dr of rho to the 1/5 plus gradient of Laplacian inverse of rho equals 0. Okay, so here I'm just sort of, instead of writing this as 1 over rho gradient of rho to the 6/5, I'm writing it as dr rho to the 1/5 with some constants you have to worry about. But okay, I think this is what you get here. Make sure I have to say pressure. It's 1 over 18 rho to the 6/5. Okay, and now I'm going to linearize by letting rho be rho LE plus epsilon sigma, and u just be epsilon u, and then I formally take epsilon to 0. And when you do that, the first equation, what you get is dt sigma plus divergence of rho LE times sigma equals 0. And the second equation, what you get is dtu plus, this is epsilon squared, and so it'll just go away. When you linearize this, okay, sorry, I think this should be a 1/3 now. Sorry, okay, if you linearize this, you end up getting a 1 over 15 dr of rho LE to the negative 4/5 times sigma. So if I linearize rho to 1/5, I get this. And then plus gradient Laplacian inverse of sigma is equal to 0. Okay, this is some system. It looks a little bit nicer if we take a time derivative of the second equation. And when we do that, we get dt squared u. And then, okay, so there's a 1 over 15 dr rho to the negative 4/5. And then dt sigma is minus divergence of rho LE sigma. So right, divergence of rho LE sigma here. And I pulled the negative sign out here. And when you take dt here, you end up getting gradient Laplacian inverse of divergence of rho LE sigma. And all those operators cancel out. And so here you just get minus rho LE sigma is equal to 0. And now this is pretty nice because there's no more non-local terms. And it looks sort of like a wave equation because we have dt squared and then dr of divergence, which is related to Laplacian. It's not quite formally symmetric. And so what we do is we're going to call u hat to be rho LE the 1/2 times u. So we're going to multiply this whole equation by rho LE to the 1/2. And when you do that, you get dt squared of u hat minus 1 over 15 rho L to 1 half dr rho L to minus 4/5 divergence of rho L to the 1 half applied to sigma minus, oh, sorry, this should be U here, minus rho LE. Sorry, this should also be U. Sorry, for some reason I'm putting sigmas here, but these should be U's. Because what I'm doing is I take dt of sigma and I have divergence of rho E times. Sorry, this should be U. Sorry about all these typos. But hey, dt sigma plus divergence of rho U equals 0, because if I linearize this, U is size epsilon, and dt of rho is dt sigma, epsilon sigma. Okay, so these should be U's. So this equals 0. U hats. Okay, but the point is that this looks like a wave equation. And so I'll move back over here. And so what you get is you can write this new, so the linearized system is equivalent to the following. So you have dt squared of U hat. Hopefully I had 2 dt's over there. Okay, yes, I did do that part at least correct. Plus, I'm going to call this operator H hat U hat equals 0, where H hat is negative 1 over 15 rho E to the minus 1 half sorry, it's plus 1 half dr rho E minus 4/5 divergence of rho LE 1 half, and then minus rho LE. Okay, and this operator is now formally symmetric. If you take the adjoint of this entire thing, it'll be symmetric. Okay, so now I'm going to talk about properties of H hat. So first of all, so there's an unstable eigenvalue. Or so, I mean, I'll say negative eigenvalue. And the way to think about this is that it's because 6/5 is less than 4/3. So if we kind of go by these heuristics over there, we're in the unstable range. And so it turns out there's a single unstable eigenvalue. One way to see this is that you can actually write down an element of the kernel using the scaling symmetry of the system. And when you do that, this kernel element will pass through the R-axis once. And so by Sturm oscillation, you know there should be one unstable eigenvalue. Okay. And this actually is sort of similar. So that's one thing I'll note. This is similar to the linearization of negative dt squared. Actually, I want to have positive dt squared of phi minus Laplacian of phi minus 5/5 equals 0 about phi equals 1 over 1 plus r squared. 1 half. So, okay, this is the energy critical semilinear wave equation in 3D. And there's the same exact static equation. And so you have the same static equation solution. And if you linearize this, you again see there's one unstable eigenvalue. Okay, and so, okay, this sort of, okay, suggests that if you ever want to sort of, okay, understand the dynamics, you should first understand the dynamics of this negative eigenvalue. And anything else you do, you should sort of have to work around this. But okay, another property though of H hat is that so as r goes to infinity, the speed of sound, so CLE, so this is rho LE to the 1/10 power because gamma is 6/5. And this is going to be 1 over 1 plus r squared to the 1/4. And this is like 1 over r to the 1 half as r goes to infinity. And so in particular, this kind of principal term is not asymptotically the Laplacian. Instead, so as r goes to infinity, if you sort of compute out what happens, you have that H hat looks like here you end up getting negative dr squared, or sorry, the point is you get 1 over r dr squared minus 1 over r squared dr. And if you do this correctly, you get plus 1 over 4 r cubed. So this is sort of what happens to this term. Okay, plus some lower order terms, and then you get plus, and this other term is 1 over r to the 5th. And so that's also lower order. So sort of the main thing here is you get this, maybe plus, I'll try this lower order terms. Okay. And so, yeah, what I'm going to talk about today is the case where we're going to consider a codimension 1 set of initial data, which does not activate this negative eigenvalue. And then the problem is, okay, question is sort of, okay, are you then stable? And one way to think about this is you should look at the decay rate of this wave equation, at least when you're sort of not activating this eigenvalue. And you get this kind of funny looking operator. Okay, and maybe one comment here is that this is a big difference between this from maybe this example here, from dt squared phi minus the Laplacian of phi minus phi to the 5th equals 0. Okay. So now, okay, I'm going to talk a little bit more about this operator. Yes.
We talked about the eigenvalue, but what space does the eigenfunction? Specifically, what are the R weights?
Right. So this operator h hat, this is symmetric with respect to just the R2, like integral of things with respect to r squared dr. And the eigenfunction is decaying very exponentially fast. Yeah. Any other questions? Okay. Yeah, and so if you, okay, so I said the speed of sound was like 1 over r to the 1/2, and that means that if you sort of draw what the characteristics look like in the TR plane, what you end up getting is that they're going to sort of curl up like this. Okay, and so our first step to looking at this wave equation where you have this sort of leading order behavior at infinity is to straighten out these cones. So we straighten this out, we call a new variable y. And you're going to change variables so that these become straight at infinity. And the idea is that we want 1 over r to the 1/2 dr. This should be dy. And if you sort of check what this means r and y should be, this means you want 1/2 dr equals dy. And so I think you want, if you integrate those 2/3 r to the 3/2 by. So you call a new variable y, which is r to the 3/2. And when you do that, your variable looks like this. And then, so in terms of y, as h hat goes to infinity, what you expect is that h hat, this will now look like negative dy squared. Then if you sort of plug this in and you sort of compute what happens to the lower order terms, you end up getting minus dy, and then plus 1 over 9 y squared. Plus lower order terms. Sorry, this should be a 1 over y dy. Okay, and so in particular, this looks like, so this is, looks asymptotically like a 2D wave equation. Because you have this dy squared minus 1 over y dy with an inverse square potential. With a good sign. Okay, and so if you're very familiar with inverse square wave potentials, you know that sort of the coefficient in front of the 1 over y squared matters a lot. And in 2D, the sort of critical threshold happens when that coefficient is 0. And so because this has positive 1 over 9 y squared, that's good for dispersive properties. Okay, and so in particular, because the 2D wave equation, this means that we expect u to decay like t to the minus 1 over 2 as t goes to infinity if you have at least nice initial data that does not activate the unstable eigenvalue. Okay, And so in particular, if you define u tilde to be y to the 1/2 u hat, then u tilde is O of 1 as t goes to infinity. Okay. Okay, so now, now this is some heuristic for understanding the decay rate of the associated linearized equation. And the next thing to do is to see, okay, how does this interact with the nonlinearity? So now we're gonna plug this into nonlinearity. And so maybe a model for this, or like kind of the way that dispersion can change sort of how you expect the nonlinear dynamics to work is if you take a 3D wave equation. So let me take this example. Let's do it, John, I think, 81, where you take tt squared phi minus the Laplacian of, minus 1 plus dt phi, Laplacian of phi equals 0. Okay, and so in this case, since you're a 3D wave equation, this tells you that that phi will decay like t to the minus 1, at least if you pick with very nice data. And so in particular, sort of r phi is bounded at the linear level. Sorry, so everything here I should say is at the linear level. Okay, and now, so this means that maybe if you want to think about sort of the dynamics for this, where if you take very small localized potential data, what you should do is you can maybe let phi tilde be r times phi. And when you plug this into the equation, you get dt squared of phi tilde minus 1 plus dt phi tilde over r, Laplacian of phi tilde equals 0. In particular now, sort of, sorry, okay, I should write this as dr squared phi tilde. So okay, if you take the 3D wave equation, you look at this variable, then you just have transport equations. But now your nonlinearity is now this tt phi tilde over r. And now if you now look along characteristics, so the claim, and so I'm not going to kind of go into details at all, is that so d phi will obey the following Riccati equation. And so, okay, I should also mention that everything I'm talking about right now is in radial symmetry when things are a lot easier. But you end up getting something that looks like, I'm sorry, maybe I want d squared phi here, d squared phi tilde. This is going to obey some sort of Riccati equation like x dot equals x squared over t. And so you should think that for Berkeley's equation, you just have the normal Riccati equation, x dot is x squared. But because there's this 1 over r here, when you look along the characteristics, you have r is like t, and this gives you this 1 over t factor. And okay, if you let x of 0 be epsilon, then you solve this, and you see that x is infinite when t equals O of e to the 1 over epsilon. Okay, and so in this case, the way that, so what dispersion does is it delays the shock from the singularity formation mechanism. And so instead of having a 1 over epsilon here, you have e to the 1 over epsilon. But there still is blow up for this problem. And okay, you should also think that this is a model for if you take irrotational isentropic compressible Euler around a constant density state. And then so that sort of means you should interpret this as shock condition. And there's been a lot of works about this outside of radial symmetry. Yeah, I'm not going to summarize that right now. Instead, I'm going to sort of try to use this heuristic now for our equation. I'm going to go back to Euler-Poisson. Back to Euler-Poisson. Okay, and now I'm going to drop law of terms. So I just want to sort of present a heuristic. But the way you should think is that the momentum equation will look something like dtu plus, and then there's this transport term where you have CLE plus u. This is the speed of one of the characteristics, where the speed of sound plus u times DRU is equal to 0. And now this looks like Berg's equation, but we want to change variables into variables that are sort of going to be essentially obeying transport equations, since we know that u is going to have some decay rate. And so the first thing I'm going to do is I'm going to say, okay, so before I had this variable u hat, which was rho e to the 1/2 times u. So I'm going to change to u hat, and u hat is so at least asymptotically as r goes to infinity. This is r to the minus 5/2 u. And when you do that, you have dt of u hat plus CLE. So actually, I'm just going to replace now CLE by r to the minus 1/2 plus r to the minus 5/2. Oh, sorry, so this now becomes r to the 5/2 u hat, dr u hat equals 0. So, okay, maybe I'm dropping some terms, but you shouldn't really worry about them so much. And so here u is r to the 5/2 times u hat. So that's what's going on here. And so this is already looking a little bit like that example where we sort of pick up some factors of r here. The next thing we want to do is we want to change from r to y. As a reminder, we have r to the minus 1/2 dr equals dy. And when you do that, you have dt u hat plus, and then here I'm going to pull out r to the minus 1/2. So I'll get dy of u hat equals 0. And here you get 1. And here you have r cubed. Sorry, no, you get, yeah, I think r cubed u hat. Sorry, but r cubed, okay, and so remember, r to the 3/2, 2/3, r to the 2/2 equals y. And so, okay, I don't really care about constants here. So this means that r cubed is actually y squared. Yeah, y squared. So, okay, so if you switch to y, you get dtu plus 1 plus y squared u hat, dy u hat equals 0. So, okay, right now I'm just sort of doing some change of variables. And finally, I'm going to change from u hat to u tilde, which is y to the 1/2 u hat, because this was a variable that I said sort of takes into account this t to the minus 1/2 dispersion rate, and will kind of be O of 1 at t goes to infinity. So kind of morally, this is the closest to satisfying a transport equation at infinity. When you do that, you have dt of u tilde plus 1 plus y to the 3/2 u tilde dy of u tilde is equal to 0. And so in particular, in this case, we had a 1 over r that sort of delayed the shock formation. But now we end up with a positive power of y here. And this is sort of an artifact of the fact that our sort of background was decaying very fast. And so, okay, we had to conjugate variables to sort of take this into account. Okay, and this means you expect shock formation at t equals O epsilon to the minus 2/5. Okay, and our work now is to make this rigorous and to justify this mathematically. But the idea is to sort of firstly kind of prove that this kind of shows up for this model. At least if you kind of ignore the nonlinear instability, then you get this sort of accelerated shock formation. We say accelerated, this is better than epsilon to the minus 1. And also another idea is that sort of once we know how to do it for this model, then we kind of can use these similar heuristics to look at kind of more interesting models. Okay, so I'm now going to talk about some results. I'll start by mentioning some previous work. Actually, maybe I'll save that up there for now. Okay, so I'll mention now some previous work. And let me get my notes, make sure I get the dates right. Okay, so first I just want to talk about kind of general stability of stars, at least in the mathematical literature. A lot of this stuff has been looked at for a long time in the physical literature, but in terms of sort of rigorous results, there's this work of Lin, right, SS Lin in 97, who looked at the linear stability of these vacuum stars in Lagrangian coordinates. In particular, sort of this statement I'm making here, where if gamma is bigger than 4/3, you're linearly stable, and less than 40/3 unstable. This is in this paper. There's also this work of Rain in 03, who showed sort of a stability statement. Sorry, I should say nonlinear here. So nonlinear stability when gamma is bigger than 4/3. And there's also, okay, there's many other works. One recent work is due to Cheng and Lin, and Yulin. And this is in 24. And in this case, they also look at now nonlinear instability for 6/5 less than or equal to gamma, I think, less than 4/3. Okay, there's a lot of work here. One thing I want to mention is that a lot of this is sort of in the framework of weak solutions. To the Euler-Poisson system, and so they kind of the frameworks are sort of insensitive to shock formation, and so like, for instance, like the way that they kind of show instability in some of these cases is to show there exists an expanding solution very close to the Lagrangian star, but this expanding solution can include shocks they mention in these works. A work that's much closer, sort of in terms of methods, to what we're talking about. This is actually due to one of my collaborators, Juhi Zhang, in 08, where she showed linear or nonlinear, sorry, instability when gamma equals 6/5. And so in particular, what she shows is kind of related to this unstable direction, where it shows that due to this linear instability, you have sort of this like growth in norms. If you look at the nonlinear problem for gamma equals 6/5, and this is a bit tricky because you have because the speed of sound is decaying, you're sort of approach this vacuum region, so you have to be very careful in the spaces you use. And so, yeah, our methods are sort of inspired by some of the frameworks sort of developed in this work. So I guess I should also mention, this is kind of one direction. For gamma equals 4/3 exactly, this is the mass critical case. There's also been a lot of work here. And sort of one thing is that separation of variables is very effective. Okay, and so in particular, these works by Goldrick Weber. Fu Lin. This is in 98, I guess. Makino in 91. Okay, and they also show that sort of near the Lagrangian star, there are these expanding solutions and contracting solutions. And yeah, there's also been much more work here. Okay, but now, okay, now I'm going to talk about our results. Results. I'm going to sort of state this as 3 theorems. So theorem 1. is, let's say linear theory. And so what we show is that the linear energy space decomposes as a 1D stable space plus a 1D unstable space plus a center, or can I also say codimension 2 center space. And so the point is that H has one negative eigenvalue. And so if you now look at the wave equation, you're going to get an exponentially growing mode, which is this unstable space, an exponential decaying mode to the stable space, and everything else. And on the center space, sufficiently nice data. Has that y to the 1/2, or maybe I'll just say u tilde, converging to a radiation field. Okay, and so in particular, we justify this t to the -1/2 decay, which you sort of expect from the heuristics, and show, okay, this you can measure this pointwise, and if you multiply by y to the 1/2, then you're going to have some convergent to some limit object as you look kind of far enough along these characteristics. And you should think that this is sort of kind of what you need in order to set up this shock formation argument. Because I guess, at least for in this sort of regime, it's really, you can kind of think about this sort of, yeah, you read off sort of where the shock occurs from the radiation field. And it's because sort of you allow dispersion to happen for a while, and then that sort of leads into the shock formation. Okay, theorem 2. This is so nonlinear long time existence. Okay, and so yeah, maybe I should erase something. Okay, maybe I'll draw a picture somewhere. Maybe I'll draw a picture over here. Okay, so so here I'm going to say that we have this. So this is the unstable direction. So sigma plus is unstable. Do you think there's a unstable direction? There's a stable direction. Okay, and then there's this sort of center speed. So sigma 0 is the center. Okay, and so for instance, for this problem, you can show that using sort of different methods that your solution must exist to at least time O equals epsilon to the 1/epsilon, O equals e to the 1/epsilon. And so we have a similar statement here. So for sufficiently nice rho 0, U0 obeying linear orthogonality conditions. We want now to so that it's center stable. Stable. And a sufficiently small modulation. I'll call this phi plus. You should think that phi plus sort of is kind of some small sort of width in the vertical direction. So here our data is going to sort of lie in this space. Then the solution. Okay, sorry. There exists some C1 depending on phi naught, depending on rho naught U naught. So that the solution to Euler-Poisson with data you take rho LE plus epsilon phi naught and epsilon U naught, and then plus epsilon times this other small thing. So phi plus. So this exists for t equals C1 epsilon to the minus 2/5. Okay, and then finally, theorem 3. For fixed, so it's kind of similar setup as before. For fixed rho naught U naught with non-trivial center component. So here we want there to exist some radiation field to trigger the shock, and so that sort of corresponds to the fact that there is some your coordinate sort of along this axis is non-zero. Then we sort of have, okay, then there exists like capital C1 sufficiently large, or okay, there's just some C1 so that for epsilon sufficiently small, sorry, I should say here this holds for epsilon sufficiently small. Okay, then the solution with, I'm going to sort of assume the same data with data as above, exhibits gradient blow-up at time t equals capital C1 times epsilon to the minus 2/5. So the statement is sort of the statement that actually, okay, you do know what the blow-up looks like at this time scale. Okay, so maybe I'll now briefly talk about some aspects of the proof. So maybe I'll say aspects of proof. Okay, so kind of step 1 is to do the linear theory. Okay, and the idea is that we have kind of the first thing we do when we look at this, so this is all about this operator h hat, which is sort of this funny elliptic operator. So the first thing we do is we prove integrated local energy decay. Okay, and this is kind of maybe you should so sort of our kind of so we kind of using spectral methods, using spectral information. Okay, and so this is the point is we have this variable coefficient operator, and sort of this is a weak form of dispersion, which is one way to sort of start looking at dispersion. And this is sort of inspired by kind of these works of Tataru and collaborators. Okay, in particular, there's this kind of work 08. There's kind of more works here. Okay, the second thing is then to try to sort of upgrade this to pointwise decay, and for this we use this RP method of Defermos-Ronyansky. And then there's this modification for inverse square weights. And so I think here there's this paper of Gaik. Okay, and but the point is sort of these are kind of some robust tools that have been developed to kind of justify the statement that we have convergence to a radiation field. Okay, maybe actually I want more space, so I'll move back over here. Or maybe I'll just kind of stick near here. So very quick kind of comment on the nonlinear part. It's a nonlinear argument. Okay, so for this, we first kind of pick T1 so that there is linear dispersion, divergence to radiation field. And so I y in here. So there's some time T1 that depends on the initial profile, but is independent of epsilon, so that okay, at this point, you expect your solution, at least at the linear level, to be close to the radiation field. So this is sort of region A. In region A, you use linear theory. Like epsilon being small to close. Okay, and then so then sort of, at least for a linear wave equation, you expect that your solution at this point will be sort of from then on concentrated in this outgoing light cone from the origin. So I'm going to split kind of, so okay, now there's this other time t equals of epsilon to the minus 2/5. Okay, that's regions B, C, and D. So for region B, I think the idea is to use something related to finite speed of propagation. I'm putting quotes here because, first of all, Euler-Poisson is a non-local system. This operator we wrote down over here is local, so that sort of suggests that the non-locality is not so important, at least at this kind of this part of the argument. It's important for showing the existence of the steady state with this nice decay rate at infinity, but sort of the rest of the contributions end up being sort of lower order. Maybe another reason why we can't just say finite speed of propagation is that we also need to do a modulation. And so, okay, that could also sort of break finite speed of propagation, at least if you just kind of say it in the most explicit way. But the idea is that, okay, you should expect things are small here if you start very concentrated to the origin. In method C, in this case, so we use the successful method of geometric coordinates, kind of pioneered by Christodoulou. And here we integrate along characteristics. Okay, and as maybe another comment, we kind of deal with the inverse square interaction. So maybe one kind of difference between this case and just the case that I raised with the 3D wave equation is that for 3D wave equation, you really have that once you multiply by R, you have transport equations of radial symmetry. But here, okay, there is some like 1 over R term, but okay, part of what we do is we sort of take care of this term. And then region D, so here, the idea is to use, so I guess peeling properties. Of the wave equation. Okay, and so actually this is another sort of thing that we show at the linear level, is that sort of, okay, for the normal wave equation, you expect that your solution will just be concentrated here, but we know that for other wave equations, we should still have some sort of decay as you go inside the light cone, and so that's something we have to show, but the point is that this is what's going to sort of stop anything bad from going here, but you also need to modulate to get rid of the linear instability. That's a comment that, okay, sort of the initial data that we're considering with this problem is sort of kind of very close, so sort of very close to this space. And so you're going to have to sort of pick your modulation parameters to avoid triggering this. But yeah, I think I'm over time, so I'll stop. Thanks for listening.